within a fault, it's different near the surface than it is down deep. If you think about the difference in pressures and difference in temperatures, it makes sense. Near the surface, low pressure, low temperature, the grinding that happens breaks up the rock, we get that breccia, and we also get gouge. Gouge is just finely ground, kind of like flour. It's clay and silt particles that are being ground by the fault movement, but nothing really is happening to them. There's gravelly chunks, there's fine dust, and it sits there and fills in the fault. As we go deeper to higher pressure and higher temperatures, in the 5 to 10 kilometers deep, so we're talking deep by any kind of mining or even drilling standards, we're getting into the cataclastic areas where the chunks of rock are now acting almost like ball bearings and rollers, helping allow movement, but there's so much pressure that they're not just loose breccia chunks. Then as we go even deeper, below 10 kilometers, higher than 250 degrees Celsius, the rock is starting to metamorphose due to the high pressure and high temperature. And we're getting into mylonites. Mylonites are fine-grained metamorphics that happen in a fault zone. Down around that deep mylonite zone is the deepest that we can actually get earthquakes. Once we get past a certain point, there's too much heat, too much pressure. The rock simply doesn't break. It just bends and flows. So there's no earthquake below a certain point. Now, one thing that's kind of key is that the scale here on the right makes it look like this maximum depth for earthquakes might be 14 kilometers. That's not accurate. Not everything here is to scale, and this temperature to depth ratio changes from place to place. 300 degrees Celsius might be at 12 kilometers where this drawing was. In another part of the world it might be at 2 kilometers. Another part of the world it might be at 40 kilometers. It varies tremendously. So the maximum depth for earthquakes is based on pressure and temperature, and so it'll vary anywhere from maybe 15 kilometers in certain settings all the way down to 60 kilometers in other settings. Listric faults can happen with a normal fault, but they can also happen with a reverse fault. You can see here, same kind of curvature, but these are reverse faults. The key is that the dip decreases with depth, and it's the stress, that pressure or tension, depending whether it's reverse or normal, is rotating the plane of the fault. So you have one block sliding and some rotation happening because of the curvature of the fault. One of the last things to talk about, I know covered a lot of material today, is the role that fluids play in a fault. They can play a major role. Sometimes they are a dominant feature. I mean, sure, there's tectonic stress, but determining whether the fault releases and there's motion, or that stress builds up, is often very, very dependent on fluids. Water can enter pore spaces that are opened up in a rock by faulting. So you get a fault, it allows water in, which allows more faulting. Kind of a positive feedback loop. Pore pressure in the fault drops relative to the surrounding rock. You figure, there's water in all of the rock. You open up some space because you've got faulting and there's a crack. Water is coming out of the surrounding rock and filling the fault. It's at lower pressure. As more groundwater enters, because hey, it's a low pressure zone, water, any fluid actually, moves from the area of high pressure to the area of low pressure. Therefore, more and more water is flowing into this fault zone. This can trigger more and more movement. We call this fault valving or seismic pumping. Fault valving and seismic pumping being just synonyms, two words for all of this groundwater flowing into the fault zone. The way fluids affect fault motion can be seen in something called the beer can experiment. Unfortunately, being distance students, I can't really do this with you. I have tried in semesters past to do a video recording of the beer can experiment to provide. It hasn't worked all that well, so I'm just going to talk about it and explain it to you guys. The famous beer can experiment did start by some scientists that were hanging out, having some beer after work, and being curious and playing around with their beer cans, and they noticed something. They noticed that sometimes if they had a surface, here it's a pane of glass, could be a tabletop, but anyways, a surface, in certain circumstances, they had to have it very tilted for the beer can to slide down. That's like, gravity representing the force, the stress, and then the beer can sliding down it representing motion along the fault. Other times they could have it just barely inclined, therefore there's not much gravitational force that's trying to slide the can. Most of it's force holding the can down, but the can would still move. So what on earth would make the beer can slide easily at a shallow slope one time and not move until they raised it up to a steep angle other times? Well, the answer is actually back in image B. The guy is putting his can in the freezer. When you put a can in the freezer, or in the experiment, we actually set the cans in a bunch of dry ice to get them really cold really fast. The air inside that can also gets cold. Air is a fluid, just like water is, but it expands and contracts a lot more because it's a gaseous fluid. The can itself is the pore space. So if you have a rock with a little gap that's filled with fluid and it's cold, then you heat it up, that fluid expands and there's pressure inside the pore pushing outward. This is going to help things break, it's going to help things move. In the beer can experiment, they have the can in the freezer, the air inside the can is cold, they set the can out on their glass or their table, air inside the can starts warming up as the room temperature air heats the can, which heats what's inside of it. If the can is oriented with its opening down, then that pore pressure is pushing the can, lifting the can slightly off the table. It can slide around, almost like a little hovercraft. So they don't have to tilt the glass much. On the other hand, if they don't do this, they have to tilt the glass pretty steep before the can will move at all. Pore pressure made the can slide easily. Pore pressure makes a fault slide easily. And you can see in the bottom right, they've been doing their little beer can experiment for a long time and they're really happy.